Okay, a moment ago we had taken the given function f of x comma y equals x cubed y and the vector v 4 comma 1, and we found the directional derivative of f in the direction of a vector u, and u was just the normalized version of v, right? Now let's actually find the directional derivative of f in the direction of u. Um, if the vector, the direction we want to go is 1 comma 0, and then let's also repeat the experiment, find the directional derivative of f in the direction of u if the direction we want to travel is the vector v is 0 comma 1. So note that the vector, so there's two questions here, apologize about that, so read before the word um, and the vector v equals 1 comma 0 is already normalized. So what's the normal vector we need? U is just 1 comma 0. And if we take to compute the directional derivative according to our new formula, we should dot the gradient vector, which we already found, with the 1, 0 vector. And here's the great thing. When you do this dot product, yeah, 1 times the first component of the gradient plus 0 times who cares what the second component of the gradient is. You just get 3x squared y. Notice that this was actually what f sub x was, right? Like, remember the first component of the gradient vector was the partial derivative with respect to the first variable x. So we already got this 3x squared y. So notice this all really works out because we really just dotted with the 1, 0 vector. I mean, we multiplied the partial derivative we're looking at here with the number 1, and then we did plus 0 times who cares what. To answer the other part of this question, look at the vector v is now, we're changing up what vector v is. Let's say it's now 0 comma 1. It's already normalized, so we're going to use u is 0 comma 1. And when we dot the gradient with the 0 comma 1 vector, we only get the second component, right? We only get x cubed. And again, notice that f sub y is x cubed. It also was x cubed, and you might say, oh, what a coincidence, but actually think about what we just did. We took the gradient and we dotted with the 0, 1 vector, so no wonder we got the second component, not even stretched out, not even multiplied by 2, right? It's literally just we got the second component, we got x cubed back. So this always happens. I mean, this always happens. It's not something special for this function. I hope this one example convinces you that this always works out this way. If you just need to do another example to convince yourself, you should do so. But the point is, if the directional derivative, if you're looking at in the direction 1 comma 0, then the directional derivative is the same as the partial derivative with respect to x. If the direction vector that you want to do the directional derivative is the vector 0, 1, then the directional derivative is the partial derivative with respect to y. It should always work out this way. So here's the thing, though the directional derivative, as we had seen, was defined in terms of these two partial derivatives, maybe I shouldn't say defined, but is at least computed in terms of these two partial derivatives, the directional derivative itself generalizes these basic partial derivatives to any direction we want. So up until before these slides, we were able to just compute how does z change if you move purely east or purely north. Now we can move in any direction and still ask how does z change. So what is the directional derivative of, oh, okay, now we're talking about a function with 3 input variables. But I hope the same general idea applies. We would call, I guess, w the output variable. But f of x comma y comma z, 3 input variables, equals x y squared plus y squared sine z plus x cubed sine 2z. I'd like the directional derivative of this function at the point 3, 1 pi over 2 in the direction of 2i minus 3j plus 6k. So 3 input variables, but I hope it's not too, even though we haven't gone through all the formulas in careful detail, it's exactly what you think should happen. All the same principles apply. We take the vector that we were provided. It was in the IJK notation, but of course we could have set an angle bracket 2 comma negative 3 comma 6. Here's the magnitude, happens to be 7. Turned out to be a whole number if I did my calculations correctly. So we take the vector v and we scalar multiply by 1/7, and I already pushed that 1/7 in. The vector u should be 2/7 comma negative 3/7 comma 6/7. Take that as our unit vector. The gradient looks like this. I won't, again, go through all the details of it, but just compute partial derivative with respect to x, with respect to y, with respect to z, and then we need to take this thingy and plug in 3, 1 pi over 2. So it looks like that. Sorry, it looks a little messy. It sort of jumped. I wish the equals were aligned, but let's not worry about that here. I did not bother talking through all the simplification, but this gradient evaluated at the specific 0.31 pi over 2 ends up being 1, 8, negative 18 if I didn't make a mistake. Of course, you could, if you'd like to, write that in IJK notation as well. Now, the thing we need to do is just say, well, I hope no surprise, to get the number, which is the directional derivative, we dot this 1, 8, negative 18 vector with the unit vector 2 sevenths, negative 3 sevenths, 6 sevenths. Yeah? So you do this dot product for fun. I just happen to write this in the IJK notation for both of these. And when you do, 1 times 2 sevenths plus 8 times negative 3 sevenths plus negative 18 times 6 sevenths, you get a thing that looks like this. That number happened to be negative 130 over 7. Now, I hope I've made no silly mistake of, some differentiation that I did may perhaps slightly incorrect, or some typo or arithmetic error or whatever. But assuming all things are correct here, the directional derivative is negative 130 over 7. Now, for the interactive question, give a one-sentence interpretation of how this number negative 130 over 7 relates to the point 3, 1, pi over 2 and the function f, focusing on what the number negative 130 over 7 means geometrically or situationally, physically, create some kind of example where the w value, I guess we should call it, right, the output of this function has some meaning, and then provide some kind of physical interpretation or geometric interpretation. Just kind of dig into what this should mean, but you should bring into your story 3, 1, pi over 2. You should probably bring into your story the vector 2, negative 3, 6. And you should certainly bring into your story the number negative 130 over 7.